Hello student, welcome back to lecture series on Fourier transform. For more videos, check in my I button. Here in I button you will get all my videos there. Okay, in my yesterday's lecture I explained to you all linearity property for Fourier transform. Okay, so our today's lecture we go for the change of a scale property. Okay, so what actually change of scale property and how we can prove this one. Okay, so let's get dive into our today's lecture. I'm gonna explain to you all change of a scale property here. Okay, yes, let me write the change of a scale property. So the statement for change of a scale property, it says that if capital F of S is a complex Fourier transform. Okay, so already I explained complex form of the Fourier transform, okay, in my last lectures. So if capital F of S is a complex Fourier transform of small f of x, then we write capital F over f of ax, which is equal to 1 upon a f of s by a. Okay, so that means this one we can write this way. Okay, Fourier transform of f of ax can be written as 1 upon a f of s by a. Okay, this one is a change scale property. Okay, so how the actually that property is coming, let me explain the proof of this property. Okay, we go for understanding what is the logic behind of this property. Okay, yes. So for the proof of this property, as we can see that it seems like that capital F curly braces f of ax it is there. Okay, that means we have to apply Fourier transform, definition of a Fourier transform. Okay, and what the definition for Fourier transform, it says that, let me write, by definition of Fourier transform, by definition of a Fourier transform. Okay, so we apply the definition of a Fourier transform. It says that capital F S, okay, we write capital F S, or we write capital F under curly braces small f. Okay, small f of s, small f of x we consider. Okay, small f of x. Okay, which is equal to integral over minus infinity to plus infinity. Okay, that small f of x it is we are taking. Okay, e raised to I s x dx. Okay, so this one is our definition or formula for Fourier transform. Okay, that one I'm going to apply here for solving our change of a scale property. Okay, yes. Now see that what we have, capital F of s. Okay, so we go for the replacement of value, as we want capital F over small f of x. Okay, so we consider this side first and try to get the another side. Okay, using this Fourier transform. Okay, now replace small f of x. Now see that this quite seems like equivalent. Okay, that means capital Fourier transform out here, small f of x, so we replace f of x as a small f of x. Okay, now see that how I'm going to prove this property. Capital F as it is outside, okay, under curly braces small f of x. Okay, small f of ax and curly braces complete. Okay, f of x I replace as a small f of ax. Okay, which is equal to, okay, now see that minus infinity to infinity integral, it remains same. Okay, so I'm going to apply this integral over our given Fourier transform definition. Okay, and small f of x we have f of ax. Okay, so what we have, f of x, small f of x as a f of ax here. Okay, yes, f of ax, that bracket f of x I replace f of x as we have f of x here. Okay, e raised to isx, e raised to isx dx here. Okay, e raised to isx dx. Now see that guys, we have to solve this integral further. Okay, now this one is a function f of ax. Okay, that means function under function it is there. So whenever we have function under function or function to the power function, okay, function divided by function, in such a case under integration we apply substitution method. We apply substitution method for solving our integral. Okay, yes. Now see that what is the function under function f of ax. Okay, that means ax it is the term that it is here as a function under function. Okay, so we replace ax as some value. Okay, I consider ax as a t. Okay, let's consider ax as a t here. Okay, I consider this ax as a t here. Okay, yes. So if you are going to replace ax as a t, that means you are replacing the variable x which actually matter with the dx. Okay, so you are replacing ax here as a some another variable, so you must have to replace that x also and that dx also. Okay, yes, so if you want to replace that dx, you must have to take its differentiation. Okay, if you want to replace that dx, you must have to take this differentiation. Okay, so you will get the dx here. Okay, now see that you have to replace x also. Okay, so x can be written as using this one. Okay, let me write x here. This implies x can be written as t divided by a. Okay, x can be written as t divided by a here. Okay, this one is the value for x, which is a t by a. Okay, yes, so I got the x, I got the ax. Now it is the time to find out the dx. Okay, yes, now see that we go for the differentiating this term with respect to x, so you will get the dx. Okay, so ax having a differentiation with respect to x, which is a only. Okay, now see that x having differentiation with respect to x, which is only a. Okay, and the in differentiation of a t with respect to x, which is a dt divided by dx. Okay, we are differentiating with respect to x now, so x having differentiation a and t having differentiation dt by a dx. Okay, yes, so we want the value for only dx. Okay, so apply variable separation here, so take dx here, a at the denominator, so we write the value for dx which is equal to dt divided by a. Okay, we write a dx which is equal to dx, take here a, take again to the denominator. Okay, so we write dx which is equal to dt divided by a. Okay, so we replace this dx here, we replace this x here, and ax which is equal to t here. Okay, so replace all these values. Okay, now see that how integral our look like, minus infinity to plus infinity. Okay, f of ax, that means f of t, we write this one as a f of t. Okay, yes, this one is our f of t. Okay, yes, and e raised to isx, e raised to I. Yes, what is the value for x? What we have here, x is a t by a, replace x as a t divided by a. Okay, yes, x I replace t by a, and dx can be written as dt by a. Okay, dt divided by a. I hope you all have understood how I have replaced all these values in our integral. Okay, because it is x f under f ax, it is there. Okay, and we are trying to reduce our quantity f over s by a. Okay, so that's fine, go for the substitution. And now see that 1 upon a, which is a constant, take it outside, 1 upon a outside here as a constant, minus infinity to plus infinity, it is integral, it remain as it is. Okay, yes, so keep f of t also as it is. Okay, yes, now next step what we do, take that a to the denominator of s, as we have integral with respect to dt, so we take that t free from here. Okay, yes, so f of t e raised to I s divided by a. Okay, e raised to I s divided by a, and t outside here. Okay, okay, e raised to I s divided by a and t outside here, and the dt remain as it is. Okay, I hope you all have understood how I have written these terms. Okay, yes, this is the actual value for capital F. Okay, Fourier transform over small f of ax. Okay, that means ax I replace as a t here. Okay, ax I replace as a t, so you can write instead of ax as a t also. Okay, yes, now see that this is 1 upon a, minus infinity to plus infinity. Okay, f of t e raised to I into s divided by a t dt here. Okay, try to compare this integral with this integral. Okay, yes, now see that minus infinity to plus infinity, it is there. Okay, yes, small f of t, we have capital small f of x as it is here, e raised to I times s replaced by s by a. Okay, s replaced by s by a, and instead of x we have t and a dt here. Okay, instead of dx it is a dt here. Okay, yes, so this one is the value for f of s. Okay, this one is the value for f of s when s it is itself a s. Okay, and when we have f of s by a. Okay, so we write this one as a this term. Okay, this term s by a as a f of s by a. Okay, f of s by a. Okay, so we write this one as a f of s by a, this entire term as a f of s by. Okay, so see that f of s by a can be written as minus infinity to plus infinity. Okay, f of t, okay, f of t as it is here, e raised to I times s by a t dt. Okay, so if you compare these two sides with these two sides, you can understand it. Okay, so this one is the actual value for f of s by a, so I'm going to replace this f of s by a here. Okay, yes, so next step, it look like 1 upon a as it is, that 1 upon a constant as it is here. Instead of that integral, we write f of s by a. Okay, capital F of, that means Fourier transform over s by a. Okay, so as you are defining Fourier transform over s as a e to the power s, I times s. Okay, that means you have to define your Fourier transform over s by a as e to the power s by a here. Okay, so instead of a dx, you can take dt also, or any another variable. Okay, it doesn't matter. So we write capital F, okay, Fourier transform, okay, over f of ax. Okay, f of ax can be written as 1 upon a capital F over s by a. Okay, yes, I hope you all have understood, guys, the proof of a change scale property. It's not that difficult, it is one of the easy property, guys. Okay, just need to understand the logic behind of the property. These are the important properties for solving the example. Okay, so for your reference, you can check my entire solution over here. Okay, change of a scale property, okay, statement here, the proof it is here. Okay, yes, this one is the entire proof for our statement. Yeah, I hope you all have understood, guys, my entire solution. It's not the difficult, it is one of the easy proof. Okay, yes, so even after, if you found anything difficult, confusing, guys, let me know in my comment section. Change of a scale property, it is one of the easier. Okay, yes, so in our next lecture, we go for the remaining property. What we have remaining property? Shifting property. Okay, so in my next lecture, I will explain to you all shifting property. Okay, so for that, we'll wait. Okay, so thank you everyone, thank you for my today's lecture.